Okay, if we're going to solve the system by graphing, which is our only means to do these problems right now, we want to go through, we want to graph each equation in the system. So if I start with this first one, I put it in a form that I can graph with, like slope-intercept form. I'm going to bring it down here. I'm going to solve for y. If I solve for y, subtract x over, divide through by 3, we'll have negative 1/3 x plus 5/3. If I graph using slope-intercept form for that equation, graph that line, well, let's start with the 5/3 here, my y-intercept. That's 1 2/3, right? So if I go up to 1 2/3, plot a point, kind of approximating here, there's my point. From that point, I have to travel down 1 and over 3 because of the slope. So down 1, over 1, 2, 3. There's my second point. If I draw my line, let's get this set up here. There's my line that represents the first equation, x plus 3y equals 5. Okay, focusing my attention now on the second equation. Do the same thing. I'll solve for y. Solving for y here, quickly, I could just add y over, right? And subtract 3 over. I'd have 2x, subtract 3 over minus 3, add y over. This would be y, right? Want to rearrange it. Y equals 2x minus 3. But from here we can see the y-intercept is negative 3. The slope is 2, so up 2 over 1. Got my 2 points, draw my line. Let's make this red. Okay, I've drawn my 2 lines for the system. Now we want to solve this system. To find the solution, we take the point of intersection, right? Now, part of the problem with graphing is that this isn't always real precise, right? But if you had to estimate an ordered pair to represent the solution, what would the ordered pair be? Looks like it's lining up here with what, 2? And maybe with 1? Would that be a logical ordered pair? Okay, so I could say my solution is the ordered pair 2, 1. Now if I wanted to check and see just how well I did with that solution, I could take x is 2 and y is 1 and plug back in, right? Plug in here, here, plug in here, here, and if it works for both, then I know I've got the right solution. Does that point work for both? I think you'll find it does. Plug in 2 here, right? 2 plus 3 times, plug in 1 here. That gives me 5. Plug in 2 here. You got 2 times 2, 4, minus 1 here. That equals 3. So even though the graph might have been a little bit rough, okay, we had to estimate a little bit. Came up with the right solution. Now, in addition to solving these, we want to be able to classify these. So if I'm going to put a classification on this, what's the classification? Okay, it's consistent because it has a solution, and it's independent because it has one solution. That'd be the classification. So with what we know right now about solving systems, as long as we know how to graph lines, we can do this, right? So let's try another one. a system of 6x minus 3y equals 9 and 2x minus y equals 3. Using the same kind of approach I did on the first one. I'll take my equations, I'll set up slope-intercept form for the two equations. I bring this first equation down, solve for y, subtract 6x over, divide through by negative 3, gives me positive 2x and minus 3. Got my slope-intercept form for the first equation. If I plot a point on the y-axis at negative 3 to represent the y-intercept, then from there utilize my slope going up 2 over 1, plot my other point, and draw our line through that set of points. That should work. Now, same thing, taking the second equation, solving for y. Well, second equation solving for y, I can do that trick just like I did with the previous one, right? Add y over, subtract 3 over. If you do that, this equation just turns into 2x minus 3 equals y, or y equals 2x minus 3. If you go to plot that equation, or plot that line, well, we go down to negative 3 again, right? Plot a point. We go up 2 over 1, plot a point, and you can get a sense of what's going to happen here. You got the same line. If you have the same line, then you have infinitely many solutions, right? Now we need to think about a way to maybe express that. Infinitely many solutions. We know that all the points on this line are a solution. But if we wanted to generalize one point to represent that, what we could do is we could set up an ordered pair, and we could set up an x here. Say, all right, that x, that's going to represent all the x's on this line. But if we wanted to set up a y in terms of that x, like say for instance, x was going to be 2. If x was going to be 2, how am I going to find the corresponding y? Could you go back and maybe plug into one of these to figure out the corresponding y? No matter which one I plug into, right, the solved form here or the solved form here, that y is going to be 2x minus 3. So we can designate a variable for x. In this case, I just chose x. But designate a variable for x. For whatever x I choose, if I take x and I plug in, I can get my corresponding y by using this expression, 2x minus 3. There's infinitely many solutions, which means what kind of system is this? Consistent, dependent. Last example, let's start with our first equation in the system. Solve for y. Subtract 6x over. Divide by negative 3. We've got positive 2x minus 2 divided by 3, so 2/3. There's our slope-intercept form to graph with. Y-intercept is negative 2/3, so we do the best we can here to plot that. Negative 2/3 right here. From that point, utilizing my slope of 2, I'm going up 2, I'm going over 1. Draw my line. So there's the line that represents the first equation. Okay, for the second one, well, this one should be familiar by now, right? This is y equals 2x minus 3. So we know the y-intercept at -3. We know the slope up 2 over 1. We draw that line in. We can see that we've got parallel lines, which we of course knew because we've got our slope-intercept form here, and we can see the slope on both of 2. Anytime the slope is same, we're going to get parallel lines. So since we have parallel lines, we have no solution. We have no solution because these lines never come into contact. So no points are shared. Since there's no solution, if we classify the system, it's inconsistent.